All right, well, welcome back. So in this section, we're actually going to be taking a really quick little detour to introduce us or possibly remind you of the world of big O notation. So for those of you that have never seen big O notation before, it's basically a really convenient way for us to describe the number of steps that some algorithm is going to take. The idea is that all of these things are going to be eating in different pieces of information, and I want to return to you some information about how long I expect this thing to run. So if you've ever heard things like linear or quadratic or polynomial used to describe the number of steps of some process, you're actually making use of this big O notation structure. What's nice about generalizing this a little bit is that we're actually allowed to look at things that are a little bit more bizarre than simple polynomials. In particular, we can look at things like logarithms. So we can say that something is going to run in logarithmic time, which is going to be a really strong thing. Or on the other side, we can look at things that are going to be exponential. The idea is that these things take a very long time to run because there's lots and lots of steps that are going to be in play. We can also start looking at a bit more bizarre functions, so things like x log x or a square root of x log x. All of these extra functions that we know and love can actually be used to describe how many steps some algorithm is going to take. And that actually becomes really important as we begin to start to look at different processes to do the exact same thing. So in this case, the discrete log problem is its own little question. The idea is that I'm trying to find this value of x that's going to make this congruence true. We know that we can attack this thing with a brute force approach. The idea is that just keep on raising this thing to larger and larger powers until the correct output is achieved. So that gives us kind of an initial baseline that all of our other processes should probably be better than that particular approach. The way that we start to rank these things is then going to be embedded in this idea of big O notation, is that I'm going to create some new approach. It's going to take so many steps, and then I'm going to compare that to what we previously saw. If it's better than the last one, I'm going to hope that this thing is a cooler algorithm. And then we keep that process going, and it begins to snowball. Is that we really want to start looking at small little nuances in these things so we can try to glean some extra little stuff off of it to make this thing run a little bit faster. So this quest of trying to do hard problems, things that are going to be done in polynomial time are usually going to be referred to as fast, and things that are going to be exponential or worse than that are going to be slow or hard problems in this case. And there's going to be a little bit of murky middle ground between these two things, which is often referred to as sub-exponential. Okay, so let's go ahead and look at the overall definition of what's going on. So in this case, you're going to give me two functions, f and g. I'm going to say that f is a big O of function g if I have that this function g is somehow going to dominate that function f. So you can think about function f as being the smaller of the two in this case. Smaller is somewhat relative because I can give this function g any type of weight in front of it. So if I need to, I can multiply it by 10,000, and I have to go off long enough, and then at some point in time, it's going to become the dominating function. So one example we can look at is this function f, which is 3x to the fourth plus 10x squared minus a 9. I claim that this thing is big O of x to the fourth, which is actually pretty nice for how polynomials work, is that I basically just have to record that leading, you have to record that highest power. So throw away the leading term, that little 3, and I'm just going to record that x to the fourth. If I want to see what this looks like graphically, I can pull open some Desmos to see a nice graph unfold. So here's my original function, this x to the fourth function. There's a bunch of other guts with it as well. So if I were to directly compare this thing to the function g of x, which is x to the fourth, you can actually see that the red function looks like it's clearly winning. It's on top of the blue function. But if I give that blue function a little bit of extra steam, so if I multiply it all by a 4, you can see that that green function actually now is dominating the red one. It's not right away, because if I were to zoom in at the very beginning, you can see that that red function starts off below the green one, but at some point in time, the green one actually takes over and wins. In this case, it takes over at value 3, and after 3, the green one is always going to dominate the red function. So in this case, if I go back to my notes in this case, and if I resume slideshow, what this tells me is that this function f, this degree 4 polynomial, is then of big O of x to the fourth. And that's exactly how all polynomials are going to work. You look at your degree of that thing, and that's going to give you information of your big O structure. Formally, I can see that this object is less than 4 times x to the fourth as long as my x is bigger than 3. And that's what this little c and this big C are actually embedded in your overall definition. If you say something is big O of 1, that means you're actually bounded. In this case, your function f is always less than some number c in this case. That's rarely going to be something that we talk about in the world of algorithms, but it is something that I can make the connection to in this case. As I mentioned before, a lot of the ones that we're going to see are things like linear and polynomial and logarithmic and exponential, but this technically works for any function g that you'd ever want to see. There's actually a pretty slick way that we can compute these things. So for those of you that have seen some calculus before, this is embedded in the idea of a limit. So I know that function f is then going to somehow be dominated by this function g if I were to take the limit of f divided by g and see this limit as x goes off to infinity. If that limit exists and it's finite, then I'm going to say that f is big O of g. So there's a process that comes into play is that if I compare the functions f and g, if this limit goes off to 0, then I'm somehow believing that that denominator is larger than my numerator. If it goes off to some number, so in this case if it goes off to a 3, then I somehow see that f and g are going to play about the same, which is more or less what happened in this last example, is that this degree 4 polynomial should be of order x to the 4th. So that makes sense. If I want to see that actually unfold in the limit structure, all I got to do is I got to take that function f, put it up on top, divide it by the function g, which is x to the 4th, do a little bit of arithmetic, and see in fact that a 3 emerges, which tells me that this limit exists, and it happens to be finite. Therefore, my function f is then big O of x to the 4th. For those of you that have seen a little bit more calculus, we do know that these limits off to infinity can sometimes be a little bit messy, but if we use L'Hopital's rule, we can actually simplify some of this a little bit more. So L'Hopital's rule works as long as the general structure of this thing is in this indeterminate form. The idea is that I have an infinity up on top and I got an infinity down on the bottom, and I know both functions f and g happen to be differentiable. What ends up happening is that I can differentiate the top and I can differentiate the bottom and then try to attack a new limit. So if I start comparing this question of what ends up winning between polynomials and exponentials, hopefully you have this gut reaction that exponentials are worse than polynomials. But if you wanted to actually show that process, you'd have to go through and actually do one of these limits. So if I wanted to compare x squared versus 2 to the x, well, if I shove this into this little limit, so I'm going to have the x squared up on top and the 2 to the x on the bottom, this perfectly fits the bill for L'Hopital's rule. I can differentiate the top and I can differentiate the bottom, which in this case is going to fire off a 2x, and then the bottom part is going to fire off a 2x and then a natural log of 2 as well. What you can see in that case is that I'm going to have to run L'Hopital's rule one more time, which in this case is I'm going to leave that little 2x on the bottom, leaving a constant 2 up on top, which in this case, as you take x and you send it off to infinity, that limit's actually going to go off towards 0, which tells me that x squared is then big O of 2 to the x, which is actually a pretty, big jump in this case. X squared is actually big O of x squared, but I can also then be big O of 2 to the x. It's a weaker statement to make. In fact, if you were to run that exact same process and take any degree polynomial you'd ever want to work with, so in this case I'm going to look at x to the n, and then divide that by 2 to the x. If I do L'Hopital's rule a whole bunch of times, so I'm going to keep on breaking off that exponent, dropping that off in front. If you keep on doing it until it all goes away, so I'm just left with an n factorial up on top, you can still see that this big overall limit's going to go to 0. What that tells me is that any polynomial is going to be smaller than an exponential, no matter how big your power ends up being. So if you take x to the 10 billionth exponent, that's still at some point in time going to be dominated by 2 to the x. Doesn't matter how large your exponent happens to be, it still will be dominated. Same type of funny things can actually happen when you start looking at logarithms and various powers of x. So if I look at log compared to x raised to the 0.00001, I guess there's only 3 zeros there. So I take some x raised to a tiny, tiny little exponent, and I compare it to the logarithm. Your gut reaction may say, well, the log's going to grow, and that thing's going to grow, but I don't necessarily know which direction it's going to go. So if I take this natural log divided by this x raised to this tiny little exponent, do some L'Hopital's rule magic on that thing, and then do a little bit of cleanup, you can see that that's again going to fire off a 0, which tells me that this function g is then somehow dominating this natural log. And the same process that we saw before is that I can technically take this natural log, raise it to any exponent I'd ever want to. I can technically take this little x in here and raise it to the smallest little exponent that I'd ever want to take. And I would still have that natural log term is going to be dominated by that x to some power. Even if I took, let's say, natural log to the 1,000,000th power, compare it with x to the 0.00000001, the natural log is still going to be dominated. So for those of you that have done a little bit of algorithm analysis, you hopefully know that logarithms are awesome things to see. Things that run in logarithmic time are fantastic. There's just not very many of them. But a lot of the things that we look at in terms of, searching and sorting, lots of those are going to be fairly efficient, and they're going to have logarithms embedded in them. So we'll sometimes see extra logs stuck on the end of various processes. The idea is that big picture, this is going to take something like square root of n, and then there's some sort that's going to have to occur, which is going to pick up an extra logarithm. Things like that. So it's not a terrible thing to stick in a couple extra logarithms. They grow very, very slowly. If you haven't graphed a logarithm in a while, they basically look like this, and then they flatten out compared to an exponential, which is going to explode very quickly. All right, now that we have this really nice structure of this big O notation in our back pocket, I just want to take a couple minutes to really quickly kind of lay out the table of some of the algorithms that we're going to be seeing in the next couple of sections, and then really quickly kind of reference what their runtimes are going to be. And you're hopefully going to see this kind of nice progression from the original approach to slight improvements to even better improvements as time goes on. So all of these things are going to be centered around this question of actually trying to solve the discrete log problem. Later, we're going to look at things related to integer factorization and a few other processes. So we'll have these kind of nice little laundry list of all possible algorithms in play. But in this case, they're all centered around the discrete log problem. That is, I'm trying to find this very special x that's going to make this congruence g to the x, which is an h mod p, actually true. So our go-to kind of first attack is actually just to begin flinging various powers of x into this thing and hope for the best. So this is your classic trial and error or brute force in this case. So we know that if g is an actual generator, we're actually going to at some point in time kick out a value of h. So the idea is that as I raise g to larger and larger powers, at some point in time, I would expect this h to occur. We also know a little bit more information. We know that Fermat's little theorem is in our back pocket as well, and that tells me that g raised to the p minus 1 power is going to actually fire a 1. And then any power larger than that, I'm going to begin to cycle on values that I've already seen. So the idea is that once I get to the order of that thing, so this p minus 1 value, I have better have seen the actual solution. If not, I know that there's actually not going to be a solution, so I can throw my hands up and say, nope, there's no solution, and I can just politely walk away. So in this case, this actually gives me kind of a worst case scenario, which is actually going to tell me what the runtime for this thing is. In this case, I'm going to say that the brute force thing is going to run in big O of p. In this case, I'm actually referencing the number of steps based on the size of my prime that I'm given. Another thing that becomes advantageous is to not necessarily write it in this base 10 representation of the prime, but to actually connect it to bits. So in this case, I want to view this prime base 2 and somehow record the overall length. One of the ways that we can do this is we can find the prime that we're working with and then identify various powers of 2 that happen to be sitting on either side of it. So in this case, if I'm sitting with, let's say, the number of 7, I know that there's a power of 2 less than it. So in this case, there's a 4 that's smaller than 7, and then I also have an 8 or a 2 cubed larger than that. So in this case, if I know my prime is sitting between 2 to the k and 2 to the k plus 1, the brute force approach is actually going to take 2, or big O of 2 to the k. So in this case, this process is going to run in exponential time. So in the next section, we're actually going to be looking at a pretty slick collision or meet in the middle attack, which is often referred to as this baby step, giant step algorithm, which gives us our first big improvement over trial and error. In this case, we don't have to test nearly as many exponents. We only have to test about the square root of the order of them, which tells me that this thing is going to be running in about big O of square root of p log p. So you can already see that that's a pretty big improvement over this function p. So if we were to graph p compared to square root of p log p, you would see that this value is way larger than that one. So that gives me my next kind of first improvement. Later on, actually in this case in chapter 3, we're going to be looking at another process, in this case the index calculus algorithm, which is a little bit more sophisticated, requires a few more tools that we're going to have to pick up along the way. But in this case, this one actually runs in sub-exponential time, which is a decently fast way to actually solve this discrete log problem. It's still not polynomial, but it's not exponential, so we're in that little murky ground between the two. So we get a kind of a crazy upper bound in this case, and like I said earlier, we do allow for some fairly bizarre functions g, but it becomes really important as I want to start to really poke at various differences between some of these processes. Actually, based off of our second one, this baby step, giant step, there's actually another one as well. The idea is that if the factorization of p minus 1 breaks up into a whole bunch of small little primes, then the discrete log problem is actually pretty easy to solve. So what that means for us in actual implementation is that if you're going to be doing something like Diffie-Hellman or something like that, you want to use primes that when you compute p minus 1, it does not factor into a whole bunch of little things. So that's going to give us some information about some bad choices for p, as well as motivate some possible good p's